Hey there, curious minds. Ever wonder what the universe is really made of?
Mhm.
We're talking about the tiniest pieces of everything, the fundamental building blocks. And get this, our understanding of those tiny pieces is about to get a whole lot clearer, maybe even, well, flipped on its head.
It really might.
Today, we're going to take an ultra deep look into the very heart of the proton.
That's right. And forget those simple pictures you might have seen. A proton isn't some, solid little dot.
Right.
It's a whole universe of even smaller particles whizzing around and bumping into each other. And we've got a plan to see this hidden world in incredible detail.
Okay, I'm intrigued. So we're diving deep into the future of the Large Hadron Collider, the LHC. You've probably heard of it smashing protons together.
Most people have.
But we're also going to talk about something that could seriously change the game, the Large Hadron Electron Collider, or the LHEC.
The LAC. Think of it as the LHC's brand new, super-powered microscope.
Yep.
While the LHC smashes protons together to see what breaks apart, the LHEC will fire a focused beam of electrons into those protons.
Okay, different approach.
Totally different. So our mission today is to understand exactly what this LHEC is, how it's going to work its magic, and why it could completely rewrite our textbooks on particle physics.
Right.
It's not about replacing the LHC, not at all. It's about giving it a partner that can reveal a whole new level of detail.
Exactly. We want to see how this new machine will give us the most precise and complete picture ever of what's going on inside the proton, pushing the very limits of what we know.
Pushing the boundaries, absolutely.
And to do this, we've got some seriously detailed reports outlining the LHEC project and all its amazing potential. So get ready to zoom in on the smallest scales imaginable.
Let's start with the big picture then. The LHEC is designed to take us to a whole new level in what we call the energy and intensity frontier.
Energy and intensity frontier.
What's really fascinating is how it plans to use a well-established technique called deep inelastic scattering, or DIS, but with unprecedented power.
Okay, deep inelastic scattering. For those of us who aren't particle physics buffs, maybe break that down. What's the core idea there?
Sure. Imagine throwing a tiny, really high-speed dart that's our electron at a bigger target, like a proton or an ion.
Okay, a dart.
Because the electron has so much energy, it doesn't just bounce off the surface. It punches deep inside and ricochets off the even tinier things within the quarks and gluons, which we collectively call partons.
Partons, right?
And by carefully watching how that electron bounces back, we can figure out what those partons are doing, how they're arranged. The more energy we put into the collision, the deeper we can essentially see.
Got it. So the LHEC is like upgrading our dart gun to a super-powered electron cannon to see even deeper inside the proton.
Precisely. That's a great way to put it. The plan is to create a brand new, incredibly intense beam of electrons and collide it with the proton or ion beams already circulating in the high-luminosity Large Hadron Collider, or HLLHC.
HLLHC, the upgraded LHC.
Exactly. This is a huge jump in both the energy of these microscopic crashes and, just as importantly, the sheer number of crashes we can study. That's the intensity frontier part.
That sounds like some serious engineering. So will the LHC have to stop its regular proton smashing work to make room for this electron beam, or?
That's the beauty of it, not at all. The current design is really clever.
Yeah.
It envisions what we call concurrent operation.
Concurrent. Okay.
This means the LHC's electron beam and the LHC's proton or ion booms will be able to run at the same time. So we can have both electron-protonian collisions and the regular proton collisions happening simultaneously.
Wow, that's efficient.
It really is. It's
Yeah.
like having two experiments for the price of one.
That's pretty smart. So this LHEC idea isn't something completely, new. It's been around.
Definitely not out of the blue. The LHEC builds on years of research,
Yeah.
most notably the 2012 Conceptual Design Report, or CDR.
The CDR. Okay.
What we're discussing today incorporates all the latest findings and improvements since that initial plan. So yeah, it's a well-developed and thoroughly thought-out project.
Okay, so we're firing these super energetic electrons at protons. What's the big payoff? What are we really hoping to learn by doing this?
The main goal is, well, to understand the proton's internal structure with a level of detail we've never, ever had before. Think of upgrading from an old blurry photo to a crystal clear, high-definition image.
Nice analogy.
And one of the key concepts here is parton distribution functions, or PDFs.
PDFs. Sounds a bit technical. Can you break that down in a less jargony way?
Sure, sure. Imagine the proton is like a busy city, right? And the partons, the quarks and gluons, are the people moving around inside.
Okay, city people. Got it.
PDFs are like maps. They tell us the probability of finding a certain type of person, a specific quark or gluon in a particular part of the city. So carrying a certain fraction of the proton's momentum or energy at a given time, which corresponds to a certain energy scale. These PDFs are absolutely crucial for understanding any experiment that involves protons, including basically everything we see at the LHC.
So our current maps of this proton city, they're a little incomplete, maybe blurry in places.
Exactly. That's a good way to put it. While we've learned a lot from previous experiments, like HERA in Germany.
Right. HERA.
Right.
There are still significant unknowns, especially when we look at the behavior of partons that aren't carrying much of the proton's energy, a region we call small x.
Small x, low energy fraction.
Yep. The LHC will extend the range of our vision, or kinematic range, in lepton nucleus, scattering by several orders of magnitude. Just think about that. Allowing us to explore this previously sort of hidden part of the city.
Wow, several orders of magnitude. That's a huge jump in detail. What kind of new things are we expecting to see on these new maps?
Well, simulations of the LHC's capabilities, they show that we could get incredibly precise measurements of fundamental things called inclusive, neutral, and charged current cross-sections.
As well as heavy quark structure functions. Think of these as just fundamental ways the electron and proton interact. Measuring them precisely gives us direct information about the PDFs.
Okay, let's zoom in on those people in our proton city. Which partons will the LHEC help us understand better? Is it specific ones?
Pretty much everyone. The LHEC is expected to significantly improve our understanding of valence forks. Those are the main building blocks that define the proton's identity.
The core identity.
Yeah, as well as the LHeC quarks and even the strange quark. But crucially, really crucially, it will give us a much, much clearer picture of the gluon distribution.
The gluon, that's the particle that carries the strong force, right? The glue that holds the quarks together.
Exactly. You got it. And the gluon plays a starring role in high-energy proton collisions. It's everywhere.
Right.
The LHEC's extended reach, that small x region we mentioned, and the high precision it offers in measuring something technical called ln-2 at small x will be incredibly valuable here.
And that measurement tells us about the gluons.
It's directly linked to how the gluons are distributed, especially how their density changes with energy.
So we'll finally get a clear map of how this glue is spread throughout the proton, even in those low-energy small x regions.
That's the hope. That's the goal. The LHEC should clarify the behavior of the gluon PDF at small x, potentially resolving some, long-standing uncertainties from the older HERI data.
Okay.
There's even the possibility of uncovering new asymmetries in the quark-C, for example, whether the strange quark and its antiparticle, the anti-strange quark, are distributed differently inside the proton. We could measure that.
That sounds like we might be uncovering some really fundamental secrets about the proton's inner workings. Very subtle things.
Absolutely. And these super precise LHEC PDFs, which will become available after the HLHEC has finished its run.
Right, after the data is collected and analyzed.
They won't just be interesting on their own. They'll be incredibly valuable for going back and reanalyzing all the data we collect at the LHC, and also for planning and interpreting the results of future, even more powerful particle colliders.
So it's like we're not just getting a better map, but we're also refining the tools we use to understand all our other particle physics explorations. It feeds back.
Precisely. It's a synergistic effect. And it gets even more specific. The LHEC will provide very precise data on charm and bottom quarks.
The heavier ones.
Yep, the heavier cousins of the up and down quarks. This detailed data will significantly improve our understanding of their fundamental masses. We're talking down to an accuracy of maybe just 3 MeV for charm, maybe 10 MeV for bottom. That's tiny.
Why is knowing the mass of these heavier quarks so important? Does it affect other things?
Oh, absolutely. Because these quark masses are fundamental numbers in our theoretical models, the standard model. Reducing the uncertainty in their values makes our models much more precise. And this will have a ripple effect. helping us to determine the mass of the W boson, another fundamental particle, more accurately, and to better understand how the Higgs boson interacts with other particles, its couplings, both at the LHE itself and at the HL-LHC.
Okay, so it's all connected. More precise information in one area leads to improvements across the board. That's really cool. What about heavier atoms, like, say, lead? Will the LHE be looking at them too?
Yes, definitely. That's a key part of the program. By smashing electrons into single lead nuclei instead of protons, the LHEC will aim to pin down the distribution of gluons within these complex nuclei with high precision.
Inside the nucleus itself.
Exactly. Reaching incredibly low energy fractions down to x of 10 or 5, maybe even lower. This will give us unprecedented insight into how gluons behave in the dense environment of an atomic nucleus, which is different from a lone proton.
That's fascinating. We've talked about these standard PDFs, the maps, but that outline also mentions going beyond standard PDFs. What kind of uncharted territory are we heading into there?
Exactly. So, while standard PDFs give us a sort of one-dimensional snapshot, how much momentum a parton carries, the LHEC will also give us access to more complex pictures.
Your dimensions.
Kind of, yeah. These include things like transverse momentum dependent, TMD PDFs. They tell us not just how fast the partons are moving forward, but also if they're moving sideways within the proton.
Ah, okay. Sideways motion.
And generalized parton densities, GPDs. These are even more sophisticated. They can potentially give us a full three-dimensional tomographic view, showing us where the partons are actually located inside the proton, like a CT scan.
A tomographic scan of a proton. That sounds like science fiction. How will we actually do that?
Well, it relied on some advanced theoretical frameworks.
Right.
One key one is called the dipole picture formalism, which becomes particularly important at these high energies.
A pole picture. Okay.
It describes the interaction between the incoming electron and the proton, not just as hitting a single quark, but in terms of the exchange of a color dipole, essentially a tiny quark-antiquark pair created briefly by the interaction. By studying these dipole interactions in detail, using specific types of scattering events, we can reconstruct these more complex, multidimensional parton distributions like TMDs and GPDs.
So the LHEC isn't just about getting a sharper image, it's about getting a whole new kind of image, potentially revealing the proton in 3 dimensions.
Precisely, that's the ambition. And this incredibly detailed understanding of the proton structure is just one part of the LHEC's mission. It also aims to revolutionize our understanding of the strong force itself, governed by the theory of quantum chromodynamics, or QCD.
QCD, right. The theory of the strong interactions. It's known for being a bit complicated, right?
It is notoriously complicated, and the LHEC's high-precision measurements are vital for both testing our current understanding of QCD and, crucially, for interpreting the vast amounts of data coming from the LHC.
Okay.
One key area is precision tests of what we call perturbative QCD.
Perturbative. Sounds like we're making tiny adjustments to our calculations, like perturbations.
In a way, yes. Perturbative QCD is the set of mathematical tools we use to make predictions for high-energy interactions involving quarks and gluons. It works when the strong force is effectively weaker at short distances.
Okay.
It involves expressing physical quantities as a series and expansion in terms of the strength of the strong force. The LHEC's very precise measurements of how often we see sprays of particles called jets.
Jets, those are the sprays of particles that fly out when quarks and gluons smash together and then quickly turn into other particles we can see, right?
Exactly right. So, measuring single jets, pairs of jets, dijets, their properties. These measurements will provide really rigorous tests of these perturbative QCD calculations.
Testing the theory itself.
Exactly. By comparing our super accurate measurements of these jets with the theoretical predictions, we can not only check if our understanding of QCD is correct, but also help determine the fundamental strength of the strong force, a value called alphas, or A sim Z.
Alphas, the strong coupling constant.
Yes, with even greater precision. Especially looking at dijets might offer smaller theoretical uncertainties to that measurement.
So the LHEC could give us the most accurate measurement ever of this fundamental force of nature.
That's definitely one of the key potentials. Furthermore, things like event shapes, the overall geometric pattern of particles produced in a collision, will offer another independent way to precisely determine SBMB.
Multiple ways to measure the same thing, which is good for checking.
Always good.
Yeah.
And because electron-proton collisions start with, well, relatively clean initial state in terms of the strong force.
Yeah. One proton, not two colliding.
Right. The LHE will allow us to study the formation of jets and that complex process of hadronization, how quarks and gluons turn into the particles we actually see, like pions and protons, in a much cleaner environment than in proton collisions.
Cleaner studies, that sounds like a welcome change in the often messy world of particle collisions. But the outline also mentions exploring nonlinear QCD. Now that sounds intriguing. What's that all about?
Ah, yes, this is where things get really interesting, potentially revolutionary. The LNEC's ability to probe the proton at very, very low energy fractions, that very small X region again, will give us unprecedented access to potential new phenomena, like parton saturation.
Parton saturation. Sounds like we're hitting some kind of limit, like something is getting full.
That's exactly the idea. Imagine we're looking deeper and deeper into the proton at lower and lower X. The standard picture. The linear DGLAP evolution equations.
Okay, technical term.
Right, sorry. Our standard theory predicts the number of gluons should increase dramatically, almost without limit. But eventually, these gluons should become so densely packed that they start interacting strongly with each other, recombining and merging. This should effectively slow down or stop their growth, preventing their number from growing indefinitely and potentially leading to a saturation of the gluon density, a new state of gluonic matter.
So we might see our current standard theories start to break down or at least need modification in this extreme regime.
Potentially, yes. While there have been some hints of these nonlinear effects at HEA, and maybe even in heavy ion collisions at the LHC, we haven't had conclusive proof yet.
Right.
The LHEC, with its huge reach in energy and precision, offers unique ways to explore this potentially brand new territory of QCD. Discovering saturation would be a major, major breakthrough in our understanding of strong interactions.
Wow.
It can teach us how matter behaves in incredibly dense environments, perhaps similar to those found inside neutron stars, or maybe even in the very first moments after the Big Bang.
That's mind-blowing. Going from understanding the proton to understanding the early universe or neutron stars, what specific measurements will help us in this quest for nonlinear QCD?
Precise measurements of something called the longitudinal structure function, FL, over a much wider range of energies and X values will be crucial.
FL?
FL is particularly sensitive to the gluon distribution and the underlying QCD dynamics at low X. If we see clear deviations in FL from the predictions based on our current understanding, the linear DG-LAP evolution,
Just a standard picture.
it could be a strong sign of new physics, like saturation effects kicking in. The LHE is expected to provide much, much more precise FL data than we have now, across a wider range.
Okay, so we're looking for things that don't quite fit with our existing rules, especially at low X. What about diffraction and vector mesons? How do they fit into exploring the strong force?
Right. Diffraction is another fascinating area. It involves collisions where the proton remains intact after interacting with the electron.
It doesn't break apart.
Exactly. It kind of gets a glancing blow. And typically, there's a large region and angle with no other particles produced. We call it a rapidity gap.
A gap in the spray.
Yes. Vector mesons are short-lived particles made of a quark and an antiquark, like the Rho or Chade-Fecy particles. New, high-precision measurements of both diffraction and the production of various vector mesons at the LHEC will shed light on the fundamental mystery of confinement.
Confinement, right? Why we never seem to see isolated quarks or gluon, only particles made of them. Another one of those fundamental puzzles of QCD. How will these glancing blow collisions and these quark-antiquark particles help us understand it?
Well, studies of diffraction, especially what we call coherent and incoherent diffraction, give us information about how the gluons are distributed in space within the proton, not just momentum, and how that distribution fluctuates from proton to proton, or even within a single proton.
So spatial mapping again?
Kinda, yes.
Yeah.
Coherent diffraction, where the proton stays intact, tells us about the average gluon distribution across the proton's transverse profile. Incoherent diffraction, where the proton might break up into low-mass states, is more sensitive to the variations, the lumpiness within individual protons.
Interesting.
The LHEC will also expand our studies of diffractive production of jets, where you have jets produced alongside that rapidity gap, and open up entirely new channels, like the diffractive production of heavier quarks, charm, bottom, and even W and Z bosons.
Wow, diffractively producing W's and Z's.
Wow. Yeah. These processes offer different ways to probe the quark and gluon content of whatever is exchanged in these diffractive interactions, something often called the pomeron in theoretical terms.
So by studying these subtle interactions and the particles they produce, we can gain insights into the fundamental forces that bind matter together. It really sounds like the LHC is a powerhouse for understanding QCD.
It truly is a unique probe, but its scientific reach doesn't stop there. The LHC also has a significant program focused on the Higgs boson.
Ah, the Higgs boson, the particle that gives mass to, well, many other fundamental particles. How will the LHC contribute to our knowledge of it? We already discovered it at the LHC, right?
Absolutely, the LHC made the groundbreaking discovery, but the LHC offers a unique perspective and the potential for much more precise measurements of the Higgs boson's properties.
Precision again.
Yes, thanks to its expected high collision rate, luminosity, the large energy reach, and the relatively clean environment of electron-proton collisions compared to proton-proton. The LHEC has a strong Higgs physics program, and even potentially its own discovery potential for new physics related to the Higgs sector.
Its own discovery potential.
Yeah.
That's exciting. How would the Higgs actually be produced at the LHEC? It's not proton fusion.
No. The primary way to produce standard model Higgs bosons at the LHC is through a process called vector boson fusion, or VBF.
VBF, okay.
Essentially, the incoming electron and a quark inside the proton exchange, a W or Z boson. And then these two vector bosons, W or Z, can collide and fuse together to create a Higgs boson. It can happen via charged currents, W exchange, or neutral currents, Z exchange.
Okay. And because the initial collision is cleaner, we can study the Higgs and the particles it decays into more easily, less background noise.
Exactly. That's the key advantage.
Yeah.
The LHEC will allow us to investigate the 7 most common ways the standard model Higgs boson decays with really high precision.
7 decay modes, what are they?
That includes breaking down into bottom quark pairs, BBE, W boson pairs, WW, gluons GG, tau lepton pairs, plus GC, charm quark pairs, CZ, Z boson pairs, and photon pairs.
That's a pretty comprehensive list. What kind of measurements are we talking about? Just counting them?
More than just counting. We'll be able to make very precise measurements of the rates, the signal strengths at which the Higgs boson decays into each of these channels.
Okay.
By comparing these measured rates, these signal strengths, often denoted G, with the precise predictions of the standard model, we can get a much clearer picture of how strongly the Higgs boson interacts, or couples, with each of these fundamental particles.
Couplings those tell us about the fundamental relationships between the Higgs and other particles, right? If they match the standard model prediction.
Precisely. Testing those couplings is a primary goal of Higgs physics now. And the LHC is expected to have unique sensitivity to certain couplings that are very, very difficult to measure accurately at the HL-LHC. Most notably, the coupling of the Higgs boson to charm quarks.
The charm quark coupling, that's one of the heavier quarks. Why is measuring its interaction with the Higgs so challenging at the LHC?
It's mostly about the background. The processes in proton collisions that look very similar to a Higgs decaying into 2 charm quarks are overwhelmingly frequent. It's like trying to find a needle in a haystack.
Right.
The cleaner environment of the LHC, with fewer background processes faking the signal, should give us a much better chance of actually isolating and measuring that Higgs to charm decay.
That's a significant advantage, a real unique selling point. What other unique Higgs studies could the LHEC enable?
Well, study the production of a Higgs boson alongside a single top quark is another interesting channel. This process can give us insights into the fundamental nature of the Higgs coupling to the top quark, specifically something called its CP properties.
CP properties. That relates to matter-antimatter symmetry, right?
Exactly. CP symmetry combines charge conjugation, swapping particles and antiparticles, and parity, mirror reflection. Understanding if and how the Higgs interaction violates this symmetry could point towards explanations for the matter-antimatter asymmetry in the universe, maybe hinting at new physics beyond the standard model.
Wow.
The LHEC offers potentially a better, cleaner environment to study the CP nature of the top Higgs coupling compared to the LHC.
And what about the possibility of the Higgs decaying in, like, totally unexpected ways, ways we haven't seen yet?
Absolutely. The LHEC will also be sensitive to searches for exotic Higgs boson decays.
Mm.
For instance, decays into invisible particles that just fly out of the detector without interacting.
Invisible, like dark matter particles.
That's one exciting possibility. These invisible decays could be a window into the dark sector. Or the Higgs could decay into new light-scalar particles that we haven't discovered yet. The LHC's clean environment is great for searching for these kinds of rare or unexpected decays.
Invisible Higgs decays. That sounds like a potential gateway to understanding dark matter. Amazing. Okay, moving beyond the Higgs, the LHEC also has a strong program in electroweak physics, you mentioned.
That's right. Electroweak physics is a theory that unifies the electromagnetic force and the weak nuclear force. The LHEC will allow for very precise measurements of fundamental parameters of this theory, complementing what we learn from other colliders like electron-positron machines or the LHC itself.
Complementary measurements.
Yes, and its wide range of collision energies is crucial here. One very important feature is the planned ability to polarize the electron beam.
Polarize, that's like aligning the intrinsic spins of all the electrons in the beam, making them point mostly in one direction, right?
Exactly. You can choose the polarization, say, mostly left-handed or mostly right-handed electrons. By having a highly polarized electron beam, the goal is around 80% polarization.
Plus or minus 80%.
We can significantly influence the rates of both neutral current, mediated by Z bosons or photons, and charged current, mediated by W bosons, deep inelastic scattering. This enhanced control gives us a greater sensitivity to the subtle effects of the electroweak force, particularly the weak part.
What kind of electroweak parameters are we hoping to measure more accurately using this polarization?
Well, for example, the weak mixing angle, often called SIN-WB. It's a fundamental parameter that dictates how the electromagnetic and weak forces mix together. This can potentially be determined with a precision better than 0.1% in certain energy ranges at the LHC.
Better than 0.1%.
Yeah, really precise. And this precision will allow us to test if this angle changes or runs with energy in exactly the way our theories predict, searching for tiny deviations.
Testing the running of fundamental constants, that's a pretty deep dive into the fabric of reality. Feels fundamental.
It absolutely is. We also anticipate very precise measurements of the masses of the W and Z bosons, the carriers of the weak force themselves.
MW and MZ.
Exactly. The LHEC's measurement of the W boson mass, MW in particular, has the potential to become the most precise measurement ever made by a single experiment. This is really important, especially given some recent tensions in W mass measurements.
Even more precise than what we can get from the LHC or other dedicated electroweak experiments like at Fermilab or future E+E colliders.
That's the current projection, yes,
Yeah.
because of the unique kinematics and the clean environment. Furthermore, studying the production of single-top quarks at the LHEC, not top-antitop pairs, but just one top,
Right.
can help us search for very rare interactions called flavor-changing neutral currents, or FCNCs.
FCNCs, forbidden fruit in the standard model almost.
Pretty much, like a top quark directly transforming into an up quark or a charm quark and emitting a photon or a Z boson. These interactions are extremely suppressed in the standard model, so observing them at a measurable rate would be a clear, unambiguous sign of new physics.
Okay.
The LHEC's sensitivity to certain TQ or TQZ couplings could surpass even that of the LHG in some scenarios.
So we're looking for incredibly rare events that could point to entirely new particles or forces mediating them. And what about the fundamental building blocks of the weak interaction, the quarks, and how they mix with each other through the weak force?
Right, the CKM matrix. Charge current interactions at the LHEC, where the electron turns into a neutrino or vice versa, exchanging a W boson, offer a way to precisely measure certain elements of this Kabibot-Kobayashi-Maskawa matrix, specifically combinations involving VTD and VTs related to top quark decays.
Oh, okay.
Accurate measurements here will further test the consistency of the standard model's description of quark mixing and CP violation.
It sounds like the LHEC will be a real precision instrument for probing the electroweak force and its fundamental components from multiple angles.
It really will, a precision machine. And as we touched on earlier, the LHEC also holds its own distinct potential for discovering physics beyond the standard model, BSM physics.
Beyond the standard model, that's the frontier of particle physics, the big unknown. What kind of new particles or phenomena might the LHEC be uniquely suited to reveal?
Well, the LHEC has promising prospects for finding certain types of new particles. For example, charged scalar particles, like charged Higgs bosons that appear in extensions of the standard model, like two Higgs doublet models,
Yeah.
2HDM.
Charged Higgs.
You can also search for the production of single-top quarks alongside a very light neutralino. A neutralino is a particle predicted by supersymmetric theories, or CUACY. This specific search targets scenarios where a symmetry called R-parity is violated.
Charged Higgs bosons and neutralinos, those are some of the prime suspects for new physics. What makes the LHEC particularly good at hunting for them compared to, say, the LHC?
Again, it often comes down to the relatively clean environment of electron-proton collisions. It can be a real advantage. For example, some supersymmetric scenarios might produce a flurry of low-energy jets, particles often called soft jets.
Soft jets. Hard to see.
Exactly. They are notoriously difficult to pick out from the overwhelming background noise of standard QCD processes at the LHC. The LHEC's cleaner initial state and final state could make these soft signals much easier to detect, potentially filling gaps in the LHC's search capabilities, maybe finding light gluinos, for example.
Soft jets from supersymmetry, that's an intriguing possibility. What other exotic particles or signatures might the LHC be sensitive to?
Researchers are also evaluating the LHC's potential for discovering things like pairs of triplet fermions, another type of BSM particle. These might decay a little distance away from the initial collision point.
Ah, displaced vertices.
Exactly, creating what we call displaced vertices. Searching for these is a hot topic, and the LHC could complement searches at the LHC itself and maybe even future dedicated long-lived particle detectors like Methuselah.
Okay.
The LHC is also being considered for searches for dark photons, hypothetical, possibly very light force carriers that could mediate interactions between dark matter particles.
Dark photons, another potential link to the elusive dark sector of the universe. What about the possibility that the particles we know, like quarks and leptons, aren't fundamental, that they have their own internal structure?
That's another avenue. The LHEC could also probe for excited fermions, heavier versions of neutrinos, electrons, EORs, and quarks, the 80s, by looking for unusual patterns in their interactions, specific resonances.
Excited states?
Yes. And there's even a chance it could reveal that quarks themselves aren't fundamental point particles, but are made up of even smaller constituents, preons maybe. We look for this through the observation of unusual contact interactions at very high energies, deviations from standard scattering predictions.
So the LHEC could potentially unveil a whole new layer of fundamental reality, either by discovering entirely new particles or by showing us that our current understanding of the particles we know is incomplete. That's perfect.
Exactly. It has multiple paths to discovery.
Yeah.
And importantly, even if it doesn't directly stumble upon brand new particles itself.
Right.
The LHE's precise measurements, especially those PDFs we talked about, will be incredibly valuable for the HLHE's searches for new physics.
How so? How does measuring the proton better help the LHC find new things?
Because almost every search for new physics at the LHC relies on comparing the observed data to the standard model prediction. And those predictions depend critically on knowing the PDFs accurately. By reducing the uncertainties in our understanding of the proton structure, the LHC will make the LHC's standard model predictions more precise.
Ah, sharpening the background prediction.
Exactly. Which means the HLHC will be more sensitive to smaller deviations that could signal new phenomena. It enhances the LHC's reach for things like contact interactions, extra dimensions, or new heavy resonances. And it improves the accuracy of crucial standard model measurements performed at the LHC, like the W boson mass.
So it's a real partnership. The LHC's precision helps the LHC's discovery power. That's a really strong argument.
Precisely. They are highly synergistic. Combining data analysis from both the HLHC and the LHEC will lead to a much clearer picture overall, a clear reduction in PDF uncertainties, and more reliable predictions for the fundamental interactions happening within colliding protons.
This all sounds incredibly ambitious. What kind of cutting-edge technology is required to build a machine like the LHEC? It really sounds like it's pushing the boundaries of what's currently possible.
You're absolutely right. It's technologically very demanding. The LHC design is based on a technology called an energy recovery LINAC, or ERL.
ERL, Energy Recovery LINAC.
Yes, this approach offers significant advantages over, say, a traditional electron storage ring. It allows for the creation of a very bright, tightly focused electron beam, and it avoids some of the performance limitations related to beam effects and synchrotron radiation that can affect circular electron colliders, especially at high currents.
Energy Recovery LINAC, that sounds like it's somehow recycling energy. How does that actually work?
That's the basic ingenious idea. In an ERL, the electron beam makes multiple passes through special superconducting radiofrequency SRF cavities.
Superconducting cavities.
Okay.
Very cold.
Extremely cold, yes, to minimize electrical resistance. First, the beam gets accelerated to its final high energy, say 60 GeV, in several passes. Then, after it collides with the proton beam at the interaction point,
The collision happens.
it's not just dumped, it's carefully steered back through the same SRF cavities, but crucially, at a different phase in the radio frequency cycle.
Ah, timed differently.
Exactly. So instead of taking energy from the cavities, the decelerating beam gives most of its energy back to the cavity's electromagnetic field. This recovered energy can then be used very efficiently to accelerate the next batch of electrons coming from the source.
That's ingenious. Seriously clever. It sounds like a much more sustainable, energy-efficient way to achieve these high-energy electron beams compared to just accelerating them once and dumping them.
It is potentially much more efficient for high current beams, yes, which is important given the high power involved. But achieving efficient energy recovery is challenging. It requires extremely high-quality superconducting cavities, meaning very high Q factors that can store the RF energy with minimal loss.
High Q quality factor.
Right. The LHE design involves multiple passes of the electron beam, both accelerating and decelerating, through these cavities. This puts very strict requirements on the stability and quality of the electron beam itself. Any imperfections can lead to energy loss, beam breakup instabilities, and make the recovery less efficient.
Multiple passes of the beam through the same cavities. That sounds like it could get complicated. Is there anywhere this ERL technology is already being used or, tested robustly?
Yes, absolutely. There are several ERL test facilities and projects around the world. One particularly crucial one for the LHC is the Perle facility, currently under construction at Orsay in France. Yes, P-E-R-L-E. It's designed to be a powerful ERL testbed. It's a smaller scale ERL operating at lower energies than the LHEC, but it aims for similar high beam currents and will feature multiple passes, just like the LHEC design.
Okay.
The experience, the data, the technological solutions developed and validated at Perle are absolutely invaluable for demonstrating the feasibility and finalizing the design of the full-scale LHE ERL.
So Perle is like a working prototype, a demonstrator for the LHE's core accelerator technology. That's really important. What about the detector? The thing that will actually record all these electron-proton collisions, what are its key features?
The detector, of course, is just as crucial. It's being designed specifically to maximize the physics output, especially for studying Higgs bosons, and precisely reconstructing the scattered electron and the hadronic final state, which tells us about the proton structure.
Right.
It will likely feature a strong central solenoid magnet, similar to the LHE detectors, to bend charged particles and allow precise momentum measurement. There might also be additional dipole magnets around the interaction point to help manage the beams. And crucially, it will need very sophisticated detectors placed far in the forward and backward directions along the beamline.
These forward and backward detectors sound important. Why are they so critical for EP collisions?
They are absolutely essential. They need to catch particles that scatter at very small angles relative to the incoming beams. This includes the scattered electron in many important kinematic regions, as well as tagging the outgoing proton or its fragments in diffractive events.
Ah, for diffraction again.
Yes, and just generally for getting a complete picture of the event kinematics, accurately measuring the energy and momentum balance. The detector design is also being kept flexible, considering potential future upgrades of the LHC protons to even higher energies, like the high-energy LHC or even the FCCH proton beams.
So the detector is being future-proofed as much as possible. That's smart planning, given the timescales. What about the costs associated with such a massive cutting-edge project like the LHeC? Must be significant.
It is definitely a significant undertaking, requiring international collaboration and investment. Detailed cost estimates have been developed, drawing heavily on CERN's extensive experience with building and operating large particle accelerators like the LHC.
Right, CERN knows how to do big projects.
They do. The exact final cost will depend on the final detailed design, the industrial production phase, and the construction timeline, of course. But there are also considerations being discussed for a possible initial phase, perhaps starting with a slightly lower electron beam energy, maybe 30 GeV instead of the full 60 GeV.
Staging the project.
Potentially, yes. That could allow for earlier operation and physics results and possibly spread the costs over a longer period. It's one option being evaluated.
So a step-by-step approach might be possible. What are some of the major technical hurdles beyond the ERL itself that still need to be fully addressed to make the LHEC a reality?
While managing that energy recovery process efficiently and ensuring the stability of the very high current electron beam as it makes multiple passes through the LINAC that remains the central challenge. We need to minimize energy losses from things like synchrotron radiation in the arcs and prevent various beam instabilities from developing.
Instabilities.
Yeah.
Things that could disrupt the beam.
Exactly. Things like space charge effects, the beam breakup instability, BBU, over multiple passes, coherent synchrotron radiation, CSR, in the bends, microbunching instabilities, lots of complex beam dynamics to model and control.
Wow, sounds tricky.
Also, the design of the very intense electron source, the injector system that creates the beam, and achieving the required performance from the superconducting RF cavities themselves, these all require pushing the limits of current technology. And as we mentioned, achieving incredibly small beam sizes at the collision point, tiny bit values to maximize the luminosity of the interaction rate, is another significant engineering feat in the interaction region design.
It really sounds like a delicate and incredibly complex balancing act of many advanced technologies working together perfectly. What about the physical infrastructure? Where would the LHC actually be built? Does it need a new tunnel?
The current baseline plan is to build the LHC at CERN, making maximum use of the existing LHC tunnel and infrastructure.
Ah, using the LHC tunnel.
Yes, this would involve constructing the new electron ERL racetrack, likely tangential to the existing LHC proton ring, possibly reusing some existing underground areas or requiring some new caverns and tunnels. And of course, building the new experimental hall for the LHC detector at one of the LHC interaction points.
Okay.
For even more ambitious future projects like the FCC, an Electron Hadron Collider based on the proposed 100-kilometer future circular collider tunnel.
100 kilometers.
Yes, for that scale, obviously significant new civil engineering will be required, and initial studies for that are already underway as part of the broader FCC feasibility study.
A much larger tunnel. The scale of these future projects is just incredible, mind-boggling. One of the final topics in our outline is electron-ion collisions. We touched on it briefly with lead. How will the LHEC enable these more broadly? And what extra things will we learn by smashing electrons into heavy atomic nuclei instead of just protons?
Right. By colliding its electron beam with the heavy ion beams like lead or possibly others that the LHC will provide, the LHC will really open up a new frontier in studying the structure of matter inside atomic nuclei.
Nuclear structure at high energy.
Exactly. For the first time in a collider setting, we'll be able to perform deep, inelastic scattering off nuclei at energies far beyond what's possible in current fixed-target experiments. This will give us crucial new information about nuclear parton distribution functions, NPDFs.
NPDFs. How partons behave differently inside a nucleus compared to a free proton.
Precisely. How the dense nuclear environment modifies the quark-and-gluon distributions. We know there are effects, shadowing, anti-shadowing, the EMC effect, but the LHEC will map them out with unprecedented precision, especially the nuclear gluon distribution at small x, which is very poorly known right now.
So we're not just looking at individual protons anymore, but at how they and their constituents behave when they're packed tightly together in an atomic nucleus. What kind of new phenomena specific to nuclei might we see?
Well, we'll be able to investigate saturation effects in nuclei much more directly. The gluon density is expected to be even higher in a large nucleus than in a proton at the same X, so saturation might set in earlier or be more pronounced.
Ah, okay. A better place to look for saturation.
Potentially, yes. We can also study unique types of diffractive scattering off entire nuclei coherent diffraction, which probes the overall shape and gluon profile of the nucleus,
Yeah.
and explore novel collective phenomena. For example, there's this intriguing ridge phenomenon seen in high multiplicity proton and proton nucleus collisions at the LHC.
The ridge, this long-range correlation.
Oh, yes. Seeing if similar collective effects arise in the much cleaner environment of electron nucleus, EA collisions, could shed light on their origin. Is it initial state effects, final state effects? The LHeCAA program offers a unique tool to disentangle these questions, giving us a more complete understanding of dense QCD matter.
It really sounds like the LHEC will be a powerful tool for nuclear physics as well as particle physics, a bridge between the fields. Finally, let's briefly touch on how the LHEC fits into the bigger global picture of future particle colliders. How does it relate to other plans?
Yeah, that's important context. The LHE is seen as a highly complementary project. It's complementary to the ongoing LHE program, obviously, but also to potential future electron-positron colliders like the ILC, CLIC, CEPC, or FCCE, which are often called Higgs factories.
Higgs factories.
And it's also complementary to potential future higher energy hadron colliders like the SECH.
How is it complementary? What does it add?
The precise measurements from the LHeC, especially the proton PDFs, the strong coupling constant alphas, and certain electroweak parameters, will significantly enhance the physics reach and our ability to interpret the data from all these other facilities. Better PDFs mean better predictions for LHC searches and measurements. Precise alphas is needed for precision Higgs and electroweak calculations at E+E colliders.
So it helps make the other machines better.
Exactly. And as we discussed, a future, even larger electron hadron collider, like the FCC, possibly using the same ERL technology but colliding with 50 TeV protons, could push these disinvestigations to even higher energies, exploring even deeper into matter. The LHC is really seen as a crucial and logical next step in this global, multi-decade effort to unravel the deepest secrets of the universe.
So the LHEC isn't just a standalone experiment, it's a vital part of the international roadmap for particle physics research, building on the LHC and enabling future discoveries.
Exactly. It's a crucial next step in our ongoing quest to understand the fundamental building blocks and forces that shape our universe. It fills a unique niche.
Well, this has been an absolutely fascinating deep dive into the incredible potential of the Large Hadron Electron Collider. It truly sounds like a bold, exciting vision for the future of particle physics.
Absolutely. It really is. The prospect of mapping the proton's inner workings with, percent level accuracy, potentially witnessing new states of QCD matter like saturation, and precisely measuring the properties of the Higgs boson. These are just some of the incredibly exciting possibilities.
We hope this exploration has given you, our listeners, a good sense of the amazing science that the LHC could unlock and its important role in our ongoing quest to understand the fundamental universe. What aspects of the LHC's ambitious program do you find most compelling? Maybe the 3D proton imaging, the search for saturation, the Higgs precision. What groundbreaking discoveries do you think are most likely to emerge from this project? It's exciting to think about.
Yeah, it really is. And considering the LHE's potential to fundamentally reshape our understanding of matter, one can't help but wonder how these new insights might ripple outwards beyond particle physics itself. Could they, for example, refine our models of the universe's very earliest moments, right after the Big Bang, or perhaps help us better understand the extreme conditions, the exotic matter, found within objects like neutron stars? It's a truly profound set of questions that the LHEs, by giving us this unprecedented view inside the proton and nucleus, can really help us start to answer.